Welcome back to the Mechanics of Solids lecture series. We're looking at examples of axial indeterminate systems with thermal strains and misfits. Here's the next example that we're going to look at. We have a high density polyethylene block 1 positioned in the fixture as shown. The block is 2 inches by 2 inches, cross-sectional area by 32 inches long. At room temperature, a gap of 0.1 inches exists between the block and the rigid support at B. And we're asked to determine the normal stress in the block and the normal strain in the block caused by a temperature increase of 100 degrees Fahrenheit. This problem is relatively simple, provided that we can recognize the compatibility consideration and write a compatibility equation. Let's go ahead and summarize the given information, synthesize what was written in the text. Our givens are elastic modulus of 120 KSI, and note that this is relatively small compared to some of the materials we're used to dealing with. The coefficient of thermal expansion alpha is 78 times 10 to the negative 6th per degrees Fahrenheit. We're given dimensions, 2 by 2 inch block, so the cross-sectional area there would be 4 inches squared. The length of the block would be 32 inches. And we're given that there's a gap, delta gap equal to 0.1 inches. Okay? Then we are asked to find the stress in the block, sigma, and the strain, epsilon, at delta T equals 100 degrees Fahrenheit. Let's go ahead and record the units we're interested in. Stresses for English units typically KSI, and strains, of course, are unitless. Okay? Now, our compatibility equation for this block. Let's consider what happens if we apply a temperature increase. We apply a temperature increase, the block will expand and continue to expand until it closes this gap. As it closes the gap, we expect these rigid supports to press upon the block, and so the block will become in compression, and the greater the temperature increase, the greater the compression force that would be observed in the block. Okay? Our compatibility consideration is a condition on the total deflection or elongation of the block, and we'll call that total elongation delta. Delta is the elongation of the block. We recognize that because of the presence of this rigid support, the deflection cannot be larger than delta gap. So maximum possible deflection, delta equals delta gap. We assume, the way the problem is written, that if we apply this temperature increase, the gap is going to close. So we'll say delta equals delta gap. Now, what causes or what contributes to the deflection? We have two terms here. First, we have any force, internal force that arises in the bar would cause a deflection. Delta equals FL over AE. So that's the portion of the deflection due to internal force in the bar, plus the thermal expansion, which gives us a deflection according to alpha delta T. And the sum of those two terms would be the total deflection, and we'll set that equal to delta gap. Okay? And that's it. We don't need an equilibrium equation for this problem. All we need is compatibility, and we can use that to solve for the internal force. I'm going to again demonstrate the approach where we manipulate the equation, solve for F, and at the very end substitute in all the variables. So F is equal to delta gap. I'm going to bring this term over to the right hand side, minus alpha delta T. I'm missing an L here, minus alpha delta t times L, and then divide this by L over AE. We can go ahead and substitute in the known values, delta gap of 0.1 inches. Make sure you count for your units all the way through the problem. Alpha equal to 78 times 10 to the minus 6 per degree Fahrenheit times the 100 degrees Fahrenheit times the length of 32 inches. And this will be divided by 32 inches over AE, 4 inches squared, times E, 120 KSI. Before I get an answer here, let's do some unit accounting. On the top, we have inches, degrees Fahrenheit, per degree Fahrenheit times Fahrenheit cancels out. We have inches on top. On the bottom, we have kips per square inch times inches squared, so the square inch and the inches squared cancel out. This inches here cancels out with this inches here. So all the units cancel out except for the kips right here. And it's 1 over kips, which is going to bring kips to the top. Gives us a force in kips as we are looking for. The numbers, if you punch this into your calculator, going to get something like negative 2.24 kips. Okay, so that is our internal force. Now we were asked to find the stress and the strain. Let's go ahead and open a new page here. Stress is simply F over A, negative 2.24 kips, divided by the cross-sectional area of 4 inches squared, equals negative 0.56 KSI. Now this might trigger a little question on our part. This is a relatively small number for a stress. However, part of the reason for that is because the elastic modulus for this polyethylene material is rather small. It's more similar to rubber than steel. So that is why we get a relatively small stress in the member. It is a compressive stress, which we logically understand it to be once it hits or closes the gap. Okay, the final term that we're looking for here is strain, epsilon, which is equal to delta divided by L. Very simply, our compatibility consideration from before said that delta was equal to delta gap, 0.1 inches, and divided by the length, which is 32 inches. That gives us a strain of, I'm going to write it as 3.13 times 10 to the minus third. It's a small quantity as expected, and the units cancel. It is unitless as expected. So as far as a sanity check, both of these answers make reasonable sense, and that concludes this